Okay. Now here's the syllabus, and this has been corrected. I'll try to go through it quickly. I can't get this light off, but y'all can see it okay? Okay. It is Physics 112, Principle of Physics, Software and Blackboard supported course. Only a 2-credit hour course, meaning there is no lab. We meet for 3 hours, but that's because the summer term is compressed. Okay, normally it's 2 hours in a 16-week term, so it's 3 hours in a 10-week term, 3 hours a week. Okay, so we meet from 5 to 6:30, and I'll try to be here by 5. And I'll have to change this because at the time I did it, I didn't know we had moved. I found that out later. So I'll change this, and what are we, K? Let's see which number this is. Since everything's working here, we're going to use this one, number 114, aren't we? 214, yeah, K 214. So I'm going to change it here so I don't forget that. I won't change both of them, I'll just change one. The nursing building is the K building, and it's 214. Okay. All right. My name is Charles Fowler. That's still correct. My office on the Bessemer campus is in the A building over there, room 265. And my phone number there is 929-3449. Now, please only call during my office hours. If you call when I'm in class, I'll never hear the phone ring, so I won't answer. And I can't rely on my voicemail at all, okay? Sometimes it misses message. Sometimes it gets them, but I don't know they're there. It's a mess. So don't leave a message. Call during my office hours, and if you can't get me, just hang up and try again later during my office hours, okay? And on the Birmingham campus, I'm here on Fridays on the Birmingham West campus, okay? I think I'm pointing in the right direction, okay? And the office I'm in there used to have a phone. It still has a phone, but it doesn't work. So the best way to reach me is 929-6377 on Fridays. That is Miss Rose Saxon's phone. My office is just behind her desk. I'm in the copy room right behind her desk. And so if she's not there, I try to pick up the phone for her. If she is there, she'll yell back and say, "This is for you." So we'll take care of it that way. But don't leave a message at 6377 either, because that's not my phone. So don't leave me voice messages. They don't work. One's not my number, and the other one, I don't know if it's working. My email address is cfile@lossostate.edu. I'm pretty far behind in emails too, but I do catch up on those a little bit. Here are my office hours. On Mondays and Wednesdays, they're pathetic. From 8 to 8:30 in the morning, and from 5:30 to 6 in the evening. That's all, folks. I have an 8:30 to 11:25 Calculus 1 class, a big 5-minute break before my Calculus 2, 11:30 to 2:25, and then another big 5-minute break between, and my Cal 3 starts at 2:30 and goes to 5:25. So I go back to the office at 5:30. That's also my lunch half hour from 5:30 to 6, because I don't have time in the day to eat lunch at all. But you can call me because I bring my lunch and I eat in my office, so you can call or come by 5:30 to 6. I'll probably be there after 6 because it takes me longer than that to eat. So, but officially, that's my office hours. Tuesdays and Thursdays, much, much, much better. Okay, 8 to 8:30, that's the same every morning because I got 8:30 classes all 4 days. And then 10:45, because I only have one 3-hour class then, not a 4-hour calculus class, one 3-hour differential equation class, which is 2 hours and 15 minutes in the summer. So from 10:45 until 4:30, when I leave that campus to come over here, those are my office hours. So a big chunk of time, 10:45 to 4:30. Okay, Tuesday and Thursday. Now on Fridays, let me talk about Fridays a minute. The school is going to be closed on Fridays the months of June and July. But in May and in August, we do have Friday, the school's still open. Well, last Friday I was here on the Birmingham West campus, and this Friday I'll be on the Birmingham because that's May the 31st. That's still in May. But beginning in June, I'm not on this campus at all on Fridays. The campuses are closed. But then in August, which is the part of finals week, that time I will be back on the Birmingham West campus that one Friday in August, first Friday in August. And then I'll be there 8 to 12. All right, the course description. It's going to fly off the page. Oh, there it is. It's on here. Okay, and basically I'll just go through this quickly. This course introduces the student to basic principles of physics with an emphasis on electricity and magnetism. The course is designed to provide the student with not only a basic knowledge of electricity and magnetism, but also an understanding of real-world applications. To prepare the students to understand electricity and magnetism, additional topics include forces. We're starting our class with Chapter 5, which is forces. Now, you may or may not have a book. I don't see anyone with a book yet. They are pretty expensive, I've been told, but I think you can rent them fairly reasonably and may even be able to find them online. I don't know about that. You'll have to look into things yourself, but renting is certainly a good idea, I think. Okay, so into forces, work and energy, that's Chapter 8. Chapter 5, force. Chapter 8, work and energy. Okay? Forces, work, energy. Power. Okay? That's actually also in Chapter 8. 8.2 is power. Okay? Sound. That's Chapter 15. We'll come back to that in a minute. The atomic nature of matter. Matter is Chapter 12. Okay, we'll do 5, 8, and then 12. And then sound, wave, motion, and sound. This is sonography course, right? Okay, so sound is, wave, motion, sound is Chapter 16. Okay, so that covers that. Topics in electricity and magnetism include electrical forces and fields. That's Chapter 17, and that will be 17.3. 17.4, that's electric fields. Coulomb's law is electric forces. 17.4 is fields. And then it says here currents. 17.5 is circuits. 17.7 is series circuits. And 17.8 is parallel circuits. 17.9 is compound circuits. So that's your electrical circuits. The current, by the way, was up there in... it's in one of the earlier sections. It just doesn't show up in the title. Now, current. Electrical circuits, I just went through those. Magnetic forces, that's 18.1 and 18.2. And fields, 18.7 is magnetic forces. The field is also included in those sections. It just isn't part of the name. And then it says capacitance, and that's down here in 19.5, induction and transformers. Induction is 19.3, and transformers are, they don't have a subject title for it, but it's incorporated in, I can't think now which section, but it's in there. And so that's why we cover 5, 8, 12, 16, 17, 18, and 19. And 17, 18, 19, it's just parts of those chapters. Okay. And this is the text. The prerequisites, none. You will be using a fair amount of math. Okay? So I'd say Math 098 or higher will certainly do you in good stead. I hope all of you have at least that, right? Okay, good. Not a requirement. It says it's required by the program. That's, I think, pretty much what's required. The textbook is this one. It's as required, but however you get it, renting it, online, whatever. Applied Physics. It's the 11th edition, 2017, which means it's probably only going to be good another year or two before they come up with a new one. And it's a good idea to bring the text because I teach from the text. That way you can follow along with what we're doing, and I use examples of problems that are in the text. And that's one thing really good about the text, has great examples, okay, and problems, and works them out for you. So I also bring paper and pencil. Now, I don't care if you use ink, but I'll make confession here. When I do physics problems, I tend to make mistakes. You'll see plenty of those. So I like to be able to erase. So that's why I prefer pencil for me, but it's up to you what you use. I don't care. Okay, calculators are certainly permitted, in fact, encouraged. Some of the things you'll be doing almost require calculators, like scientific notation and that kind of stuff. So much easier with a calculator. So get you a good calculator. Your phone will do. That'll be fine. Or a calculator on your laptop or a tablet or something will do fine. Now, I don't want to go, are y'all all familiar with Blackboard? Okay, I won't go into this. I think some of the statements here are rather bizarre, like failure to use Blackboard will severely damage your ability to pass the course. Not this course, okay? I would say the proper use of Blackboard could greatly enhance your ability to do well in the course, but it won't cause you to fail, okay? Students should always check the Blackboard announcement page and task pages prior to coming to class. The only reason I can think of putting that sentence in there to see if I've canceled class or not. And guess what, folks? I'm not going to cancel classes if I can help it. Okay? And if I know something's coming, I'm going to tell you well in advance. In fact, I'll tell you right now, I do know, I think it's the second Thursday in June, I have to have cataract surgery. Yeah, I pointed to the correct eye. Okay? I've already had a cataract removed and replaced in this eye more than 9 years ago, and this one's finally gotten bad, so that's why sometimes I'm squinting at the page, because if the blood spot gets in the way, it's hard to read through. So it's sort of a pain in the neck. But anyway, I know I'll be gone that Thursday. I have another doctor's appointment. It's going to be a Tuesday morning. I'll be back in plenty of time. So that's the only two possibilities, only one real one for this course. Okay, so if something else happens, something really major and stuff, it has to be pretty major. And if it's that major, I'm probably not going to say, bring me a computer so I can send it. Probably not going to happen that way, okay? I'll just have someone, I'll contact them over here, and they'll let you know. Okay. Okay, that's the end of the other one. So let's scroll up here a little bit. Professional competencies. Students will solve problems dealing with forces. Chapter 5. Students will solve problems dealing with work and energy. Chapter 8. Students will demonstrate an understanding of the atomic nature of matter. Chapter 12. Students will demonstrate an understanding of sound. Chapter 16. Students will solve problems dealing with currents and circuits. Chapter 17. And students will demonstrate an understanding of magnetic forces of fields, capacitance, electromagnetic induction, and transformers. That's 18 and 19. We're doing so few sections in 18 and 19. There's very few questions in the test bank, so I combine them together, and that will be your last test. 18 and 19 together. The following list is a breakdown block. I wish they hadn't put that first sentence in there. You'll be given a test at the end of each unit of study. That's after each chapter except 18 and 19 go together. And the lowest test score may be dropped. In fact, I will drop it. Well, if you miss a test, that's a 0. I have to drop that one. But the average of remaining tests will be your grade. Pretty straightforward. Everything will be graded on a 100-point scale. And let's go from there. And you know the rest. 90s are A's, 80s are B's, 70s are C's. Don't go any lower. Okay? You don't want to. Okay? It won't help you at all. And that next thing there is really stupid, but whoever wrote the syllabus, the thing, had it written totally wrong. What that person said was, the instructor never rounds down, always rounds up. That was the first sentence. Second sentence read exactly like this. For example, a 79.5% will be rounded up to an 80%, which is a B, but a 79.4% would remain a C. Well, guess what? That's a round down. Okay? That's not a round up. What she just described here is a normal rounding. 0.5 goes up, 0.4 stays where it is. So I just took out the first sentence that says rounds grades normally. Sorry about that. Attendance. Try to be here. I will try to be here, but if you can't be here, I record all the stuff that's going on. It's not as good as being here because you can't ask the recording a question. You can ask me questions. You can't see what my demonstrations are. You can only hear them. So it's better to be here. Withdrawal. Now let's go back up here. Notice that D and F there? They hurt your grade point average. Okay, and you also probably won't get credit for the course. I don't know if they'll let you in this DMS program with a D or not. Maybe they will, I don't know. I doubt it. Okay, so they're not going to help you in any way whatsoever. Well, withdrawal doesn't help you at either, but it doesn't hurt your grade point average. So if it looks like there's no way you're going to get out of making a D or an F in the course, go in and withdraw. Don't pull down your grade point average for no benefit. Now, yeah, a withdrawal could hurt your financial aid, but guess what? A D or F will hurt your financial aid. If you have to repeat the course, repeating after withdrawal is the same as repeating it after a D or an F. Okay? So, check up that. Makeup work. Okay. Oh, we have to decide this. Did we talk about it last time? Do y'all prefer take-home test or in-class test? Wow. What a surprise. Okay. I'm shocked. Okay. So I was expecting that. And I prefer them too, because that gives you plenty of time to interact with the material and get it right. I don't want it to be a timed issue. I don't want it to be, one little dumb mistake will throw you all off because you don't have time to check your answer. I want you to be thorough in it. So I will give you a week to turn in your test. Okay? Why a week? 2 reasons. One reason, you always have 1 day that you can come and ask questions. I don't understand what this is asking for. Now, here's a question, though, that I will answer, but it won't be to your satisfaction. Can you do number 7? My answer will be yes. And that's all. Okay. Will you do number 7? No, I won't. But find one like it in the book. I'll do anything out of the book. Okay? So you can, even if you think you understand what it's actually about, but you don't know how to work it, find something in the book similar to it. I'll be glad to work anything out of the book. Okay? So there's one reason. You always have 1 day to ask questions. The second reason, you always have a weekend to work on it. I don't know if y'all work. I assume you do, most of you. So therefore, if that's the only time you got really concentrated time to focus on it, is a weekend, you always have a weekend to work on it. Okay, so those are 2 reasons I always give you a week to turn it in. Okay. Now, the only possible exception may be that final exam. I can't remember how the end of the term turns out. If the finals are Wednesday, Thursday, Monday, Tuesday, then you'll still have a weekend to work on it. You may not have a whole week, but you have at least a weekend. Okay. So, therefore, makeup work really doesn't make a lot of sense. If you miss a test, you weren't here that night, next time you're here, I give you the test, try to get it in. Now, here's one other issue you might need to know. I'm a pushover. So if you need more time than a week, you got it. Except for this. I don't want you still working on test 3 where I'm giving out test 4 or 5. Because you may be making some mistake in test 3 that you're going to repeat in test 4 or test 5, and you're going to get it wrong twice. So always get it into me before I pass out the next test. So that means you're going to have to, the 1 week is usually a pretty good idea, because you got 7 tests in 10 weeks. Most of them are going to be 1 week apart, so try to get them in that time. Lateness policy, try to be here on time. I will promise to, but I've got to make it from Bessemer to here. There's several train tracks to cross. So far, I found a route that minimizes the number of blockages, but there's still several there. And then there was an accident today, right up here at Wilson Road and Rutledge. At that intersection, people were stopped all around there. It took us forever to get around.
Since I get here at 4 o'clock.
What's that?
Since I get here at 4 o'clock, because I got the might as well say 4 hours commute up here.
Right.
I'll just come in and unlock. I'll get the lady to unlock the door for me.
Okay. And if you can, go on and get the cord here that connects my computer to the projector.
From the lady downstairs.
Yeah, from the lady downstairs. Okay. Right. Okay. If you would do that, that saves me a stop by that office. Like tonight, she said, "We'll be here." And I went by the office, they weren't there. So I had to go around and find the door open. Then I had to go through drawers and things like this until finally I found where she had put the cord.
I just told you need the cord.
Yeah, and you can bring it on up here. Okay. That'll be fine. And tell her we're going to be in 214. Okay, I don't think she needs to know that. She said she was going to put a board, something up, post that we were going to be up here, but she didn't. So if you will, tell her we'll be in 214. Okay, thank you. I'll try to call and let her know that too, but I'll tell her. Now, the rest of you, is 5 better than 4:30? I think you said it was, wasn't it? 5, oh yeah, for you, sure, you said it was better. Okay, because I hate that you have to come and that you're going home.
When I'm coming to work. I have to go to work tomorrow.
Right.
And then I work the weekend.
I see. Okay. But but I thought 5 was what worked out most for most people. Okay. 5 to 6:30. Okay. Academic integrity. I'll let you read this. And by the way, this syllabus is out there on Blackboard now. I'm going to have to take it off and correct the room number and put it back on. But that's all it's going to be, is just correcting the room number. All the rest of this is good. So I won't go over all this stuff. You've probably seen it before. Plagiarism, don't do it. Cheating, don't do it. Okay, get the general idea? Okay. Professional decorum, to me this is a waste of words. Okay. I don't care if you sleep in the class. Please don't snore though, because that'll be bothering the other students. Okay. So just don't do anything that's going to bother the other students. Unnecessary traffic, don't be running trains up and down the, I don't know. Eating or drinking, look, if you have to have a little caffeine to get you through the class, I understand that. My wife needs it if I'm talking to her, so by all means, that doesn't, if you spill, you're going to clean it up. Just understand that. And don't do anything that's going to bother other students. Okay? I don't see any hats, but I don't care if you wear a hat, whatever. Okay. To me, that's sort of crazy. Course concerns, if you don't think you're getting good results out of me, I'm coming too late or something like that, you first come to me and we'll see if we can work on it. Then go to the department chair. Ooh, that's me. Okay. And then we'll go to the associate dean. Then we'll go to the dean. We'll go as far as it takes to make sure things get settled. Okay, discrimination, harassment. I like to put in one other word here, bullying. I haven't taught in this building but the last couple of years, and I haven't seen anything here because I teach at night and usually nobody else is here. But on the other campus, I've seen almost nothing that would classify as harassment, discrimination, or bullying. That doesn't mean that it hasn't gone on. I hope it hasn't, but they're not going to do it in front of me. So if you sense or even suspect anything like this is happening, please let us know so we can deal with it. We want to deal with it fairly, quickly. We want to get it corrected on the spot. Okay? We don't want it happening on our campus. Americans with disabilities, if you haven't noticed, I'm hard of hearing, so I'm sort of sensitive to this. There's processes available. On this campus, Mrs. Janine McCoy Jones, there's her phone number. On the Bessemer campus, Dr. Renee Herndon, at that phone number. So people to go to, bring your documentation. They will get the information to us, and we will accommodate however you need it. But their take-home test, hey, you can work at your own pace. You can do whatever it takes. The college this is a college calendar, which basically comes right off the website. I just put the important things down here. Okay? Any questions about the syllabus? I will get it corrected, the room number. That's the only thing that's wrong with it right now. In fact, I'll go back and correct both of those room numbers. But this won't be what's on Blackboard until I get it, the other one taken off and this one put back on. So K214. Okay, and everything seems to work well here, so we'll go with this place. Are y'all comfortable facing this way and that kind of stuff? Okay. Okay. Any questions about the syllabus then? So let me save it, and we will, if there are no questions, I'll take it off, right? Okay. And that will be in Blackboard. And let me do a little bit of description on Blackboard. Now, people at home can't see my arm waving. When you have this page, the course up in Blackboard, there's a column over here of a bunch of blue tabs on the instructor side. I don't know what color they are on the student side, but they're grouped in about 6 to 8 or 10 groupings. Okay? In the first group, like the second or third one, says syllabus and book information or something like that. That's where your syllabus is now. I'll get it corrected in the new one, the corrections made in it. The one right below this is instructor information. And that's what I'm about to give you now. I'll show you what it looks like. I'm going to put my locator card there. And here it is for summer 2019. And I'll get the corrections made in it. Well, I'll tell you this. First, my name is still Charles Fowler. My phone number is that one, but that's the one. Don't leave a phone message. Just call back during office hours. And you'll see the office hours here. My email address is cfowler@austinslate.edu, and I'm the chair of the mathematics department, but I'm also credentialed to teach physics, so that's why I'm here. Okay, so all that is correct. Let's just scroll down here to see basically what my days look like. Try to be on campus every day by 8 o'clock. This is the Bessemer campus, Monday through Thursday. When we do have Fridays, the Birmingham West campus. Okay? And so I don't know if you're familiar with that. The academic building is that long building. You know, there's 4 buildings in the center of the West campus. Administration building, the B building, the C building, and the library building. Okay? So I'm in the B building. It's called the academic building. B112. It's Dr. Pruitt's suite of offices out behind the secretary's desk in the copy room there. Okay? But that's where I'm 8 to 8. We'll get to that. My office is ACE 265 on the Bessemer campus. So I'm in the office 8 to 8:30. Then on Mondays and Wednesdays, Calculus 1 is a 4-hour course, so it goes from 8:30 until 11:25. Then Cal 2 starts from 11:30 to 2:25. Cal 3 starts from 2:30 until 5:25, and then I eat lunch, okay, at 5:30 or so. In my office, so that'll be back there. Okay, that's Monday and Wednesday. 2 5-hour breaks, a 30-minute break at the beginning, 2 5-hour breaks in the middle, and then another 35-minute break at the end. Okay, busy days. Tuesday and Thursday, in the office 8 to 8:30, and then in differential equations, which only goes from 8:30 until 10:45, then from 10:45 until I leave the Bessemer campus at 4:30. I'll try to leave a little before 4:30. I was a little later today. I had to stop and get some information to the secretary there, staff secretary, about making me some copies, and it just took longer than I thought it would. But I'm office advising here and here. I'm in my office at lunch again from 12:30 to 1:30, but before that and here I'm available. And then I've got to change this to K214. If I don't change it now, I'll forget it later. So this way I'll have a reminder. 214. Okay. All right. And then after this class is over with, I'll scroll on down. And remember, Friday is only May and August. And I'm there from 8 to 12. And I don't really do a lunch. I'll just bring a little snack I eat around 11 or so. I'm usually there well after 12, but that's only 2 days that we're talking about. Okay. So there's the end of the day. Off campus sometime after 6 on Monday and Wednesday, and I'll be leaving here sometime after 6:30 on today and Thursday, Tuesdays and Thursdays. Yeah, today and Thursday. Any questions? That would be under instructor information. Okay? It's right under syllabus information. Okay. Then go down to the second group of tabs, and one of those says handouts, PPTs, that's PowerPoints, and more. I think that's what it says. Okay? And in that one, there's not much there except all the PowerPoints, really pathetic, but the PowerPoints that are from your book, and then also the YouTube video link is there. And I think that's all that's there. Okay? So do you want me to show you how to get there, or can you navigate Blackboard okay? You okay with it? Okay. All right. So that's the introduction here. Anyone else need anything about that? Oh, let me save this, because I did make those 2 corrections. Okay, so I'll get that out of the way. Okay, and that will get this out of the way. And then we'll be ready to start here. So let me take this. There's one other thing we need to talk about, and it is important. I was hoping if you had heard the video, you would already know it. But this is a different room, so it probably needs to be said anyway. 3 safety issues we've got. We're not going to be doing anything here that's going to be hazardous. But there are 3 safety issues we always have to keep in mind. Whatever classroom you're in, whatever room you're in any building, anytime, and that's usually, anyone think of what the 3 might be? Just one of them. What happened in Missouri? No.
Disaster.
Yes. Okay. Which was it? Was it Indiana and Ohio? Is that the one that they had just a swarm of tornadoes came through yesterday? So we're still in tornado season. It's usually, right now it's a little further north of us, but I mean, they got bashed badly. What do we do if we hear that alarm go off?
In the hallway.
Okay, the hallway is good, except we're 2nd story here. Better to get on the 1st floor. Yeah, there is no basement.
I mean, sit downstairs.
Downstairs, right. Yeah,
And then
1st
stairway.
floor. Now let me, oh, you're very good.
Oh, Lord.
Okay, the closest stairwell is the one back this way. It's just really close. Go to the stairwell, lowest floor, stay there. Stairwells are usually one of the sturdiest parts of the building. Concrete, metal, all in there. So, and walls are close together, lots of corners. Those are usually pretty safe. The only thing not safe about them if there's any glass in the windows, and there's not much. So stay away from the glass, but the stairwell is good. Other than that, the hallway. And the thing that makes the stairwells sort of good is that usually if there really is an imminent emergency with weather, you're going to lose power. So the rooms don't have power, but we also have glass, so we want to get out of those. Usually the stairwells and the hallways have emergency lighting, so you won't be in the dark. Okay? Actually, restrooms are not too bad as long as there's no windows in them, because the walls are close together. Just not the ideal place to spend a couple of hours, especially without emergency lighting. Okay, so, but yeah, the stairwells, if there's no glass in them, and the hallways, if there is glass in the stairwell. Okay? So we go low interior. And since there's no basement here, we go to low, and on either side you got glass, so the hallway is the safest, except maybe the stairwell, especially if there's no glass there. Okay, so that's external emergency, weather or something like that. Okay? What would be another of our 2 safety issues? That's one. Second? Active shooter. Now that's the one that this building worries me the most. I don't think we're going to have one, but what can we do? I have no way to lock either one of these doors. Okay? Wait, I may be wrong on that. Oh no, these are better. The one downstairs I used to be in, no way to lock them. These, once that door is closed, no one can get in. Okay? So actually this is safe. I can't even get out of this door. So that's, I can. Look at that. Yeah, but you can't get in from the outside. Okay? I've tried it once before. It just doesn't sit well. Okay. So yeah, we can close both doors, turn off the light. Oh, if we hear the pop, pop, puff sound, somebody get on the phone immediately and do either the campus police or the best number. And most of the doorways, I haven't noticed, do they have those sheets there that says where campus police numbers are? Okay, check that on your way out and see if it is. Put it in speed dial on your phone. Oh yeah, I left my phone in the car. I usually don't bring my phone with me because I don't want it going off when I'm teaching, okay? So I won't ever have my phone with me most of the time. So you'll have your phone. If you don't have the campus police on speed dial, 911 is next best, okay? Let them know what's going on. Then we secure both doors, and we get, and there's really no really safe place, okay? In the back on the campus, on the Bessemer campus, the walls are tiled, okay? So it's hard, and concrete block. It's really hard to shoot through that. These are sheetrock, okay? You can't shoot through this. Most of the time we say get right back there. I would say get further away, okay? Don't get anywhere in line of sight of the glass in the window so that you can't see in. So what I would say next best, we'll start as quietly as possible turning these tables up on end like this. So you have, it's going to be harder for the ammunition to get through a bunch of tables. And we get behind as many tables as we can get stacked up there. And that will be the safest place. Okay? We're on second floor here. There's no really safe place to escape except out the door. So we're going to lock the door and deal with it. Now, you have your futures ahead of you. Most of my life is back here, behind me. So you don't be a hero. If anything comes of it, let me try to take care of it. I was in the military. I know a few things, so not very much, but I know a few things. Don't you be the hero. Let me do it. You're the future, I'm the past. So let's deal with it that way. Okay. There's active shooter. Okay, so we have outside emergency like weather conditions, active shooter, threat. What's the third? Fire. Okay. Now let's take worst case scenario first. What if my computer blows up? Starts arcing and sparking, catches my book on fire, catches the table on fire. What do we do?
Get out of the room.
Okay, excellent. We get out of the room and let everybody else just fend for themselves, right?
No.
No. We got
no
to do
man
what?
up behind.
Huh?
We grab everybody go at the same time. We bring it.
Well, what's a better way to do it, though? Pull. Okay, we'll do two good things. One is a fire extinguisher. Where's the closest fire extinguisher? Right there. Right next to the stairwell door is a fire extinguisher. Down the hall, take a left, and it's right there before you get to the stairwell door. So if it's in this room, we take care of that. Okay? Get it to me, I'll take care of that. Okay? Oh, wait, no. Let's go back to the weather emergency. When you go downstairs, stay together, because I'm going to be the last one out of the room, making sure everybody got out. And if any of you happen to have twisted a knee or an ankle or something like that, and you're having trouble doing the stairs, I'm going to be helping you down the stairs. And when I get down there, I'm going to have the roll book. I'm going to call roll. And if we can't find you, that means we assume you're upstairs somewhere. So I go up into a burning building looking for you, or somebody else has to. We don't want that to happen. So stay together. Don't say, hey, no more class today, the building's on fire, I'm out of here. No, hang together until we know. Okay, I'm sorry, that was the weather emergency. Okay, I go back up and okay. Now, if it's a fire, we go out of the building. And again, we go to the nearest exit, which is the one back there. Okay, we took care of the fire extinguisher. What did we not take care of? Fire alarm. Now, where is the closest fire alarm here? Let me look. Right there on that door, there's one at both exit doors. That's the closest, right there, right next to the fire extinguisher. You go, one person gets the fire extinguisher, another person pulls the fire alarm. Okay? I know that all of you, most of your life, I know guys do anyway. Wouldn't it be fun to break that glass, to pull that fire alarm? So you finally get your chance, okay? So be sure you do that on the way out. Now, if the fire doesn't start in here and we hear the alarm, then we're good. Okay, so what do we do on our way out? We take it carefully. We don't rush, we don't run, we don't stampede. We go quickly that way, down the stairs, and out the door. And I believe the exit is that way. If I'm not mistaken, I don't think it opens this way. I think it opens that way. And get at least 75 feet away from the building. So if there is an explosion and the glass goes flying out, we're out of range of that. Okay? Does that make sense? Okay. So that's what we do in case of fire. And again, I carry my roll book with me. And the worst place to be in case of a tornado is trying to make it home to let the dog out. No, don't worry about the dog. Dog will take care of himself. You stay in the building. Okay? That's why I have to call roll for that one. And number two, in a fire, when we get out there, that's when I'll call roll again. If I can't find you, I have to come back into a burning building looking for you, assuming that you're in danger. So please take it carefully. I know I'm doing these fast trying to make up for lost time. So those are the 3 safety issues. Let's get started now with the real course, okay? Any questions on any of those? All right, let me get these wonderful PowerPoints up. You'll see how magnificent they are. I'm sorry if I'm being negative. No, I'm not. No, I'm sorry. Yeah, I am. Okay. All right, here we go. Physics 112, Chapter 5.
Is it 5, 2 through 3?
Okay, let me see. I think we do all of 5. 5.1. Let me just look at table of contents if I can.
On here you only have 5, 2 through 3. Then you have on the second one 3 through 6, and then 8.1.
Okay, wait. You're looking at the YouTube videos.
Yes.
Syllabus or YouTube videos?
The YouTube videos.
Okay, YouTube videos. That's where I started. So we probably on the first one we had covered 5.1 in the first day after we did, just like we're doing now. We're going to get started in 5.1 and we're going to go as far as we can. Then the next day starts wherever we left off last time. Okay, and let me tell you about that. She's looking at that, and this is a really good lead-in. When you go to the YouTube videos, you're not going to see just this term's videos. You're going to see all the videos are covering most of the materials that I've taught the course. What happens when like today will be the first video, and it'll say syllabus, just like you see a syllabus on there, right? But it's going to go at the bottom. When it goes at the bottom, I take the top one off, okay? Now, they're not going to match up exactly, but they'll come pretty close, okay? So sometimes it might be the ones at the top are the old ones at the bottom are the new ones. So you pay most attention to the bottom, but if you want to look ahead. Now, why do I do it that way? Well, a few times we've got it so Screencast-O-Matic wouldn't work. We forgot to pay the bill. Not me, but somebody in the administration forgot to send them a check, so they cut us off. A few times the whole system has gone down. The supercomputer in Huntsville goes down, and we don't have any connections with anything. Other times our local server goes down. So there can be plenty of opportunities when we lose and can't send anything out. Then I'll always have the last time I taught it, it'll already be there, and you can follow that material there, even if it's not this one. So Chapter 5 is talking about forces. Does anyone know a good definition for a force? Okay, a push or a pull, a very, very simple definition of a force. A force is any push or a pull, okay? So let me, since some of you don't have books, I'll write this down. Let me get my pen set up. Okay. That's a really simple definition. I can remember taking physical science in high school under an old football coach. He was just about to retire. He had played for Alabama and was on either the receiving or the throwing end of the longest pass in Rose Bowl history. He was as tough as a knot. People were scared to death of the guy. And he didn't play for Bear Bryant. He was before Bear Bryant, but he had a gravelly voice just like that. He said, "A force is a push or a pull." You know, that's exactly how he sounded. And you thought, don't want to mess with him. And that's exactly right, a push or a pull. When I'm pushing on this desk, that is, I'm exerting a force on the desk. And if you happen to notice that, I push on the desk moved a little bit, but I also moved a little bit. So the desk is also pushing on me, or the table, or whatever you call this. Okay? A push or a pull. Okay? Now, don't try to hit the high points here. The guy who came up with a lot of this concept here is a guy named Isaac Newton. He came up with 3 laws, Newton's laws of motion. Okay? And the first of these is called the law of inertia. But before we do that, let me give you, because they do it here in the book, some of the units for force. Now we have two major systems of measurement. The U.S. system, which used to be called the British system, and then we have the metric system as one name for it, but actually the better name is, I'm going to put that in parentheses, the SI system. SI, well, it stands for Système International, a French phrase, because the French came up with this. The French were the ones who developed the metric system. There probably were a couple of reasons for that. Number one, the British didn't use it, so they were going to use something different from the British. French and British have been at each other. They're still at each other. Brexit, They get along much better now than they used to. They used to fight like cats and dogs. Okay? The British had a really good system, but you see, Great Britain was an island nation, and they could pretty much keep everything in control. France was a big, spread-out nation, not big like the U.S., but still much bigger than Britain. And France, the people in Alsace-Lorraine really didn't like the people in Normandy. They didn't like the people in Brittany. They didn't like the people, in Paris. No one liked the people in Paris. So everybody was trying to cheat each other. And they were using different measures. They would be selling a bushel of this much or that much, and it varied. And it was just havoc. Well, about the time the metric system was coming into play, that was about the time the whole French system was falling apart. The monarchy was falling. The French Revolution was happening. So the scientists said, hey, this is a good time to enact a change. So they did. They came up with this method that doesn't depend on anybody's body parts or anything else. In fact, your thumb joint was approximately 1 inch. Okay? A foot was approximately the length of a foot. Okay? Of course, Shaquille O'Neal's foot would be very different from your foot, okay? So, yeah, there were some problems there. A yard was the distance from King Henry or King Edward or somebody's nose to the tip of his finger. That was 1 yard, okay? Believe me, that's what. Have you ever seen in the old fabric stores, the hardware stores where the ladies sold fabric and they were measuring cloth? They say, I want 3 yards of gingham. They would say 1, 2, 3 yards. And then they throw in a little extra in case the arm was short. Nowadays they have tables, you measure it exactly, But that's how they used to measure yards. Each one of these was a yard, okay? So that was based on body parts, which isn't a good thing to measure because different people have different sized body parts. So the French came out with the metric system, and they said the line from the North Pole to the equator that passes through Paris, whatever distance that is, take 1/10,000th of it, that's going to be what they're going to call 1 meter or something like that. I mean, it was some weird thing. That's how they came up. Didn't depend on anything but the globe, okay? And the globe is pretty consistent, okay? So those are the two things. So forces in the U.S. system, we measure a force in pounds, okay? In the metric system, we measure forces in newtons, named after Sir Isaac. And anytime, or pretty much anytime you see a capital letter as a unit, that means it was named after somebody. A newton was named after Sir Isaac Newton, who came up with the 3 laws of motion. Okay? One of the most brilliant physicists ever to live. And mathematicians, too. He developed a whole new math called calculus, just so he could explain the laws of motion. Okay, he was quite a brain. Okay. Now, what is the conversion here? They give it in the book that 1 pound is equal to 4.45 newtons. Now, that's probably not exact. They put an equal sign there as if it is exact. My guess is it's probably not exact. It's just approximately that. Okay? So in other words, a pound is more than a newton, about 4.5 times more than a newton, or a newton is between a quarter and a fifth of a pound. So a pound is a larger unit, so you would have fewer of them. Okay. Now, Newton's first law of motion. Not quite ready for it there. So what I'm going to do, and this is what I have to do because I have such poor slides here, I'm going to discard this for a moment and pull up my other slide here, and bring that to the front. And every time I do it, then I have to get my pen back, and that's going to be there. Okay? So here is Newton's first law of motion. It's also called the law of inertia. Now, what does the word inertia mean to you? Inertia. Anything? What's the first 5 letters? What does that spell? I-N-E, inert. What is something inert? What does that mean? It's not doing anything. Okay? So one thing of inertia is getting something to move. You were stationary. In order to move, you have to overcome inertia. But there's another end to inertia. If something's moving, you have to do something to get it to change its motion. So basically, that's the law of inertia, what changes an object's motion. Now, this was not actually developed by Isaac Newton. The generation before Newton, there was a guy in Italy named Galileo. Now, Galileo was the guy who came up with this first law, but he didn't formulate it quite as precisely as Isaac Newton did. Isaac Newton took Galileo's work, perfected a little bit, and came up with the law of inertia. But here's what it says. A body, and by the way, this is the law of inertia, which is also Newton's. My writing stinks, I'm sorry. First law of motion, by the way. Okay? A body that is in motion okay? Okay, yeah. I would have put something else in here. He does it later. Okay. That is in motion with the same velocity. That's with the same velocity Now, what that means, here's parentheses, at constant speed, okay, and in a straight line. Okay, I'm going to come back and explain a few things in a minute. I'm just going to write it down like they have it here. Okay? And a body at rest continues at rest unless an unbalanced force acts on it. I don't like this definition very much because he left something out. No, I'm sorry. I left it out. A body that is in constant motion, that is in motion, I got that part right, continues in motion. That's what I left out. Continues in motion. That's why I kept looking. I said, this is not a good definition. Okay. Okay, say again. Okay. A body that is in motion continues in motion with the same velocity, that's a constant speed, straight line, and a body at rest continues at rest, both of those unless they're acted on by an unbalanced force. Pretty wordy, a lot of blah, blah, blah there, right? Okay, here's what we mean. Okay. Let's start with the motion part. Let's just imagine that I had a bowling ball here. I'm going to take that bowling ball and roll it down the floor here. Not a good idea, because somewhere at the end it's going to bang into the wall and probably dent the wall, and I'll be in big trouble. But let's just imagine we got something down there to stop it. Well, that ball is going to continue in motion, straight line, constant speed, unless it's acted on. Unless you stick your foot out there and kick it, then you make it go in a different direction. So that's what the first law is, the law of inertia. That means it's not changing its motion. If it's in motion, it's going to stay in motion. If it's at rest, it's going to stay at rest until you kick it and make it move. Okay? So you've got to do something, have an unbalanced force. Now let me back up a little bit, because we're starting in chapter 5, and some of this stuff is explained in the earlier chapters. You're certainly welcome to read those earlier chapters, but there's a lot of reading there, so I'm going to try to fill in the blanks. Okay? Let's start with a concept of distance. That's pretty easy. How far it is from there to there. That's the distance, right? Okay, it's just some measure. Now, if I was measuring this way or that way, it doesn't matter. It's the same distance, right? Like if I drove to Bessemer this morning. I'm going to drive home from Birmingham. But if I was yesterday, I drove home to Bessemer. At the beginning of the day, I drove from Bessemer to home. And as long as I went the same route, it's the same distance, right? But here's another concept. Displacement. If I was going from here to there, I've now displaced myself. Now, that's the same distance, right? But now I've given a direction. And if I turn and go back to the same thing, same distance, but now a different direction. Okay? That's what we mean by displacement. A distance is just a scalar quantity, how far you went. A displacement is how far you went, that distance, in a given direction. A different direction is a different displacement, even if it's the same distance. Okay? So, one of those, the first one, distance, is just a scalar quantity, just a number. The displacement is a number with a direction. That's called a vector. Okay, that was one of the easier chapters. Now, you don't need to know this except for what I'm going to say later. Okay? Now, you'll find we do this in physics all the time. Once you have a concept down, distance or displacement, well, what happens with the time rate of change of that? How is that changing over time? Now, if I was going at a constant speed, and someone give me your approximate thing for what that distance is from where I am to where I was before, from here to there. What's that, about 8 feet? Just to give it a number. Maybe not quite that far, but close to it. Okay, 8 feet. Okay. The distance is 8 feet. The direction would be 8 feet in whatever direction I'm facing now. I have no idea. I'd have to think about it. Just give it a direction. That would be the distance or the displacement. But if I also, with my clock, measure the time it took me to get from here to there, distance divided by time, what's that called? Speed, right? Distance divided by time is speed. Displacement divided by time, that's called velocity. So that's why they say here velocity, and then parentheses, a constant speed in a straight line, meaning not changing the direction. Okay? So that's why velocity is speed in a given direction. So there you have it. The units are the same. Displacement will be measured in feet, inches, meters, centimeters, kilometers, miles, whatever you want to do, furlongs, whatever. Your time is measured in seconds, minutes, hours, whatever you do there. So distance or displacement measured in length measurements, and that could be meters, inches, feet, yards, miles, kilometers, any kind of length measurement you want, centimeters, millimeters, I don't care what. When you take length and divide it by time, now we get meters per second, miles per hour. Miles per hour, that measures speed, right? Kilometers per hour. Anything that is a distance measurement divided by a time measurement, that is a speed or velocity. So the speed is a scalar quantity, meaning just a number, whereas velocity, I can't spell it, velocity, okay, is a vector quantity. Oh, isn't that nice? Speed, scalar, vector, velocities. They start with the same letters, don't they? And this would still be length divided by time, but with a direction. So you can't tell by looking at the units whether you're talking about speed or velocity. You have to know the context. But if it's in a given direction, that means it's a velocity. Okay? Well, once we've got a velocity or speed down pat, we say, well, let's take another derivative. Oh, I'm sorry. Take another change of rate, change of velocity per change of time. You take this and divide it by time again, and that would give you something like meters per second, or feet per second. And we often call this one a meters per second squared, just so we don't have to write 2 per second, or feet per second squared. This is called an acceleration. Okay. Either in the metric system, SI system, or the other. So, throwing a lot of terms at you now, these were all covered in the earlier chapters. We're going to need these later. Okay? So, since we had velocity, constant speed in a straight line, that means constant speed, same direction. Okay? So, you can change an object's speed by speeding it up or slowing it down. You can change an object's velocity by speeding up, slowing down, but also by changing direction. So you see, when you change direction, that's also an acceleration. We're going to get to that a little bit later, but don't worry about it now. Okay. So, can I erase this slide? Y'all got it? Everybody? It's not much of a slide. It's a jumbled mess. But get used to it. This is what you're going to see. Okay. All right. All right to erase? Everybody got it? All right. Now, what is inertia? That's where we started before. Inertia is the property of a body that causes it to remain at rest if it is at rest, or to continue moving if it's moving. Okay? It's that tendency to keep doing the same thing that's been done before. Okay? And that's with a constant velocity, meaning constant speed at a constant direction. Unless an unbalanced force acts on it. Oh, I meant to say that before. What do we mean by an unbalanced force? That would be you reaching out there and kicking it with your foot and making it change its direction. Okay? Or it's sitting there and I kick it to make it start moving. Okay? You don't have to kick it. You can hit it. You can throw it. You can do anything to it. Think about most sports. Okay? Basically, you have an object like a ball or something, and you're going to do something to that to make it change its inertia. Okay? To change its thing. That golf ball is at rest, and it stays at rest until someone hits it with a club. Sometimes I miss. I don't even play golf much, but whatever. But if you hit it, then it's going to change its inertia. It was at rest, now it starts moving. Okay? Until and unless an unbalanced force acts on it. Okay? Well, you might say that ball doesn't just take off and keep moving forever. It never come down. it comes down. Well, guess what? There's an unbalanced force making it come down. Guess what that force is? The force due to gravity. That's an unbalanced force acting on that ball. No matter what you do, shoot a basketball, you shoot it like this, but it goes up and comes back down, right? Only time that doesn't happen is when you dunk it, and I can't dunk it, and there you just go in one direction straight down. But otherwise, you shoot it, it goes up and then comes back down because gravity is pulling it down. Okay, you're throwing it up, but it comes back down. Gravity is an unbalanced force. Okay. So, that's what inertia is. That tendency to keep its current state of motion unless it's acted on by an unbalanced force. Okay. Now I think we can go back to my other slide. And we'll go to this guy pushing on the box or the crate or whatever he's pushing on. Okay? Now, obviously, he's pushing. You can tell he's grunting. Okay? You can almost hear him grunt. And it may not be moving, even though it's expressed. Okay, I'm going to push on this table. I'm going to push on this table. It's not moving, but I'm still pushing, right? Well, why? Because there's a force pushing back at me. Now, there's no wall over there that's here, but there's all this gravel, friction on this graveled surface here that's making it hard to push. So friction is your unbalanced force that is keeping him, well, in this case, he's pushing, but there's an equal force pushing against him, so there's no motion. Okay? If he finally pushes a little bit harder and gets it to move, now he can overcome its inertia and overcome the friction and get it to move. Okay? So that's what we mean by this is a balanced force here. If the frictional force equals his push force, he's not going anywhere. But if he pushes harder than the friction force, then he can get it moving. Okay? So that's what we mean by an unbalanced force. If he pushes harder than friction, he gets it to move. Change its velocity. The pushing force and friction force cancel each other out, resulting in zero acceleration, so you have no motion. Okay? Even though he's pushing like crazy. If he's not pushing hard enough to overcome the gravity, it's not going anywhere. When I first pushed on the desk table earlier, it didn't move, and then it did. And the reason is, see, at first it doesn't move, and that is probably because they waxed the floor and waxed it to the thing. When I broke that, then it moved more easily. I bet you this one would not be nearly as easy. Yeah, it's a lot harder to do because of the friction that's there. You have to have an unbalanced force to change the inertia of the body. Okay? Inertia is either at rest or changing. So the word inert means at rest, but inertia involves if it's moving. Okay, like that bowling ball, it's going to have a good bit of inertia. You got it. Any of you watch any of the baseball games that were down at the Hoover Met, either on TV or something? Did you actually go? Mm-hmm. Yeah. My grandsons. Oh, really? Who did he play for?
They was playing the Braves.
Oh, I see. Okay. Yeah. Yeah.
3-0.
Oh, all right.
The Braves way.
Oh, I see. Sorry about that. Now, you're talking about the Atlanta Braves?
No.
No. Okay.
The
City League or something.
City.
Yeah. Right. Okay. Yeah. I was going to say I want an autograph. No. Yeah. But that catcher back there catching the ball, he's having to change that ball's inertia because it's coming at him really hard, and he has to catch that thing. Okay? Or the batter is going to try to change the ball because the ball's initial inertia is this way. He wants to change it and send it that way. Okay? So everything in sports is changing something's inertia. Okay? That's involved with it anyway. Okay. Wow. Here's the next slide, and this is many, many pages over. Still, oh yeah, something like 1, 2, 3, 4, 5, 6 pages over before we hit the next slide. Like I said, this PowerPoint really stinks. So what we'll do, go back to this one, and we'll get out of this one and go back to my blank slide. I'll fill in the gaps with it. They also show here a car. Okay? I draw really ugly cars. Whoops, I need to get my pen back. I always forget to do that. Okay? Okay, there's my car. Ugly car. Don't make fun of me. Okay. There's the car. Now, we think the car is going this way. Okay? But as it's going that way, it's meeting air resistance, right? Especially if it's going any speed whatsoever, it's meeting some air resistance. There's also friction on the road that is trying to keep the car from moving. Okay? So in order to get the car to move, you have to have the force of the tires on the road that push the car this way at a greater force than the resistive force, otherwise it doesn't move. Okay? Now cars are one thing, battleships would be another thing. Battleships are big, heavy things. You can turn those screws on the battleship and you hardly produce any motion at all. It takes quite a bit of turning before finally you get it to move through the water. So that's the general idea. You have to exert enough force to overcome all that resistance. Okay? Now, what if you put that... Okay, I'm going to give you another couple of dumb examples before I get to this one. Here's your roll sheet. Here's an eraser. Now this is a very heavy eraser, but this might not do a super good job. Okay? What's the motion of this object here, the eraser? None. It's just sitting there. It's at rest. If I take this sheet here and pull on it, what's going to happen?
It's going to move.
What? The sheet will move. How about the eraser?
It will sit still.
Huh?
It may move a little bit.
It may move a little bit, but if I pull real quickly, it hardly moves at all. Because its inertia tries to get it to stay right where it is. Okay, even though the surface it's on is moving. Now, if this was a very rough surface, it would be more likely to move. If this was really smooth, then it would hardly move at all. That's the inertia, is the tendency to keeping it there. Now, imagine that most of you at some point in your life ridden a bus before, right? Okay? If you're on that bus and all the seats are taken, you're having to hang on to a pole or something like that, you've probably been in that, or say the underground rail they have in Atlanta airport. You know, most of the time you're standing there, right? Okay, now, when that first takes off, people say, I was thrown backwards. No, you weren't. You were trying to remain right where you were. The car's moving out from under you just like that paper was moved out from under the eraser. You feel like you're being thrown back, but you really weren't. You were trying to stay right where you were. Or if it goes around the curve, you say, I was thrown against the wall. No, you weren't. You were trying to stay right where you were. The wall of the car turned in front of you, and that's why you hit the wall. You're trying to maintain your state of motion. Or you're going along on the back of a pickup truck. It's not a safe thing to do. And someone slams on brake, and you go forward. Yeah, no, you're not thrown forward. It's you're trying to maintain your motion. The truck stopped out from under you. You're trying to maintain your inertia. Okay? And that's exactly what happens. I remember one time when my lawnmower was leaking gas, one of the lines on it had sprung a leak. So I called the place and they said they could work on it. So I put it on the back of the truck. I had a little pickup truck then. I tried to chop the wheels, and that lasted for about half a block. And then the chocks came out, and then every time I stopped, wham, it rammed into the back of the cab. And when I started going again, it ran into the tailgate. And when I turned, it tried to go this way. And when I turned the other way, it tried to go that. So it was moving the whole time, trying to maintain its state of motion, its inertia, while the truck was moving. Okay? That's what inertia is. So you put that car on ice now, and now your friction down here with the tire almost disappears. And now the car is moving, and it's going to be hard. You can turn the wheel, you can hit on brakes, you can accelerate. Nothing's going to happen because it's just going either stay at rest or move just like it was, because on ice, there's very little friction to make it change its motion. Remember the big ice storm of, when was that, about 2010 or 11, something in there? That day that they said, we might get a little bit of snow today, but it's not going to be enough to accumulate. And when it started snowing that morning, it came down big time. The ground was really hard cold, and when it snow landed, it didn't melt. It continued being frozen. First car ran over it, didn't have any problem, packed it down and became ice then. The next car had more problems. After a while, remember they called it the snowcopolis or something like that. Everything stopped. No one could go anywhere. Y'all remember that? Were you in the area? Well, that's because with no friction, there was no change of inertia of the car. No unbalanced force to make it turn or do anything else. I actually saw big old strong guy. This woman was trying to climb a hill, go down a hill, I guess it was, and she couldn't control her car at all, and she was about to hit the parked car, and he came along, and he kept pushing the car because he could push, and so he pushed the car all the way down the street to keep it from hitting the cars that were parked there. He was a good Samaritan, if I've ever seen one. Okay. Because the car's inertia was going to continue right the path it was taking if he hadn't been there with an unbalanced force to get it to stop. Okay. Now, another concept that ties in with inertia is the concept of mass. Okay? Now, let's go back to my bowling ball. I'll roll the bowling ball down the aisle here. Okay? What if I did the same thing with a ping pong ball? Same difference. I don't think I'm going to worry about hitting the wall down there with that. Okay? It's probably not even going to make it there. Why? Because the ping pong ball has much less mass than the bowling ball. The bowling ball's inertia is going to be very hard to change. You could do that to the ping pong ball and change its velocity, change its motion, okay? Because its mass is much less. So another thing, mass is in many senses a measure of inertia. Okay, let me write it the same way here. Mass is the measure of the inertia of a body. Okay? If you were out there playing catch with your little 6-year-old, you're not really going to need a glove very much because he or she probably can't throw it all that hard. But if that's a teenager, maybe an 18-year-old, I think I'd want a glove because I bet you that kid can throw a lot harder than that 6-year-old can. Okay? Now, that means, that's not a very good example, because, well, that's it. So let's go back to this. I'm going to throw the ping pong ball or the bowling ball. Which one you want to catch? Ping pong ball, yes. It's a lot easier to catch because its mass is less, so it has less inertia. Okay? So, therefore, I wish this picture was in the book. You have the car there, and right next to the car, you have an 18-wheeler, which has more inertia. The 18-wheeler does. So don't go bopping in front of a car. I mean, don't bop in front of either one. But if you are, you could get away with it better in front of the car than you could the 18-wheeler, because the 18-wheeler is going to have a hard time stopping, okay? A really hard time stopping, okay? Because its inertia is much more, has to have a lot more unbalanced force to get it to change its direction, okay? So there's 5.1. No problems or exercises in it. Let's move on to 5.2. Okay? Can I erase my ugly drawings there? Okay? Y'all agreed they were ugly drawings. Thank you very much. I'm hurt by that. Okay. Now, the second law of Newton's three laws of motion is sometimes called the law of acceleration. That's why I introduced the term a little bit ago. Okay, the law of acceleration. Now, actually, Galileo had done a lot of the work here, but again, Newton formalized it a lot better. Okay? And here's how it reads. The total force acting on a body is equal to, I'm just going to put equal to, the mass of the body times its acceleration. Acceleration. Okay. Sometimes my brain gets ahead of my pen and I skip some letters. Okay. That's the law of acceleration, Newton's second law. Now let's go back to the first law. Okay? The first law says an object in motion is going to stay in that state of motion, whether it's at rest or moving, straight line, constant speed, unless acted on by an unbalanced force. Okay? Otherwise, it's going to keep moving just like it was. Now, most of the objects don't. Even with that bowling ball, if I roll it down a long enough path there, it's finally going to slow down and stop. Why? There's friction between it and the surface. Even that nicely polished surface at the bowling alley, there is some friction. You know there is because you can hear it rolling along there. If it was no friction, you wouldn't hear any noise at all. Okay? So there is some friction. Okay? Now, Newton's second law says if there is a net force acting on the body, it will change its velocity. And guess what a change of velocity is? An acceleration. Remember, velocity, change of velocity per unit time, that's acceleration. So if there is a change of velocity, a net force acting on it, that's going to guarantee there's a change of velocity. And what is that net force? It's the mass of the body times the acceleration. Okay? And that leads to probably one of the most famous formulas in nature, and that's equal to F equal ma. Now this F stands for net force. Net meaning if you add or subtract all the things from it, that's what's left over. This is the mass, and this is acceleration. So you see this here, the total force acting on the body is equal to its mass times the acceleration. Okay? Therefore, when I roll the bowling ball down the floor here, the force I have to exert is the mass of that bowling ball times whatever acceleration I give it. Okay? If I give it a little acceleration, it still could have a pretty good force because it's a pretty big bowling ball. But if it's a ping pong ball, I can give just a little bit of force to it and make it roll faster or whatever. So the force is, net force is mass times acceleration. Now, I'm going to give this example that really is more of a first law example. But there's a reason for giving it now. Let's imagine we are in an airplane, a jet airplane, traveling 500 miles an hour, okay? Straight level flight at 500 miles per hour. What's the net force acting on the plane? The net force acting on the plane. If it's going straight line, constant speed of 500 miles per hour. What's the net force on the plane? because it's not accelerating. Constant speed, not changing direction. Constant velocity, zero acceleration. Net force is zero. Now, wait a minute. You can't tell me there's no forces acting on that plane. No, I didn't say that. I said the net force on the plane. Sure, gravity's pulling down on the plane, but something else has to be pushing up on the plane. Does anyone know what that is? What gives the plane its lift? Take my roll sheet again. Okay? I'm going to hold this above my mouth, and I'm going to blow. Anyone want to predict what's going to happen to the piece of paper? It's going to come up? You're absolutely right. Okay? Now, I'm going to put the piece of paper under my mouth. I'm going to blow it. Any predictions here? It's going to what? Not going to do anything. Okay, let's see. It's going to be inert, huh? Okay. Oh, it went up too. What in the world was happening there? Okay.
The wind went up and below.
Second.
It went up and below.
Yeah, it went up there. It went up there. It goes up both ways.
It's almost like it's parallel when it sends it up.
Okay. Here's what's going on. When I blow beneath it, of course, I'm blowing against the paper, making it go. I'm exerting a force on the paper, and it makes it go up. But when I blow over the top of the paper, it comes up too. Now, why is that? Well, another guy, a little bit later, his name was Bernoulli. Now, there was a whole family of Bernoullis. They were brilliant characters. They fought like cats and dogs. They were a pretty dysfunctional family, but they were quite a family. There were two brothers, and they fussed and argued with each other all the time. The younger brother really outdid the older brother, and that made the older brother mad. They were both brilliant, okay? And one or the other, maybe both of them had some sons, and sometimes the sons turned out beating the fathers, and that really made the fathers mad, so they fought like cats and dogs. But one of the sons, I think, was named Daniel Bernoulli, and he came up with this principle that a moving fluid, the pressure exerted by that fluid when it's in motion is inversely proportional to the velocity of the fluid. Okay? So when I blow against this, the paper is slowing down the blow, and the blow is pushing it up. But when I blow over the top, now the air is moving faster on top than it is on the bottom, and the faster the velocity, the less the pressure, so it goes up. Now, think about how an airplane wing looks. And Wilbur and Orville Wright, when they were developing the first airplane that really could fly, they looked at seagulls' wings. And a seagull wing is shaped like this. What that does, the lower side is slanted down, so air pushing is going to push it up. But the upper part has a sort of a bulbous thing on the side here, and then tapers down. So the air coming over the top has to speed up to go over the top because it has further distance to go than this down here. This hits against the wing. But the air is the same, so this has to go faster. So when you increase the speed, that gives it lift. And you push against the bottom, that gives it lift. So both of those things are giving the plane lift. And that's why when the plane is going down the runway, long runway, it's picking up speed, picking up speed, picking up speed, until finally the lift that's produced by Bernoulli's effect on top and the pressure underneath lifts it off the ground. Because that airplane weighs bunches of tons filled with passengers, a big aircraft, and yet it gets enough lift finally when it gets going fast enough to lift off the ground. Okay? Now on an aircraft carrier, which is a very short runway, they have a catapult that throws the planes off the aircraft carrier. And even then, they sort of dip down. They don't reach the water, thank goodness, and make their way on up. And they're burning their engines, the afterburners, I mean everything. There's blue flames coming out the back of those planes when they're going. Now, it's a prop job that's going as fast as it can, but that's how they can work. Okay. So, force is equal to mass times acceleration. Newton's second law. Okay? Now, y'all keep up with time. Don't let me get talking too much. Okay, we go till 6:30. We got time, right? Wait, what time is it now? I'm sorry?
It's 6:47.
We've just gone over, haven't we? I'm sorry. I told y'all you need to keep up with this. Okay, we got started late though. I'm sorry, I didn't mean to. We'll start at the top of page 126. Okay, I'm sorry, I didn't mean. Y'all stop me. I'll just get carried away here. I don't usually look at my watch that frequently. Okay, good deal. And we'll get started there. We didn't get far enough to have any homework exercise, boo hiss, but get over it. We'll have plenty for next time. Okay? So we'll pick up and go from there. There won't be any of the introductory stuff, and I will do my best to get here on time next time. All right. Any questions? All right. We'll pick up and go from there.
Oh, I didn't send you a text, but.
What's that? Yeah. It's from the book, and if you ever need to, if you don't have a book, you can come up. If you got phone, take a picture of the homework problems and you can work on those. But there's none for tonight. Yeah. Okay. Good deal. Y'all are very patient and kind to let me talk on and on and on. I'll blame me being home late to my wife on you because you didn't tell me. Okay. So I'm going to go and shut this down.